And we're on. And we're on to looking at this problem, which is the first problem from the 2019 exam. So what you'll notice is it gives a bunch of metals. So it says magnesium, aluminum, zinc, iron, copper, and silver together with their 1 molar salt solutions. And while it seems like a really minor detail, this part, that 1 molar salt solution, is one of the keys to this problem, because that means that what we're going to be looking at is we're going to be looking at the standard reduction potentials. Because 1 molar is the concentration at standard conditions of a voltaic cell. So voltaic is that other word for spontaneous. So we want one that's going to happen all on its own without the help of a battery, of the highest possible voltage. It would be constructed using electrodes of which 2 metals? So when we take a look at the chart, which I've scribbled all over, of course, one thing that you notice is the large positive values are up at the top and the large negative values are down near the bottom. So if we wanted the biggest magnitude ever off of this chart, what we would do is we would use fluorine from the very tippy top with this positive 2.87, and we would use lithium down here at the very bottom with a negative 3.04, or sorry, 3.05. So that's what we would do if we wanted the biggest voltage that we possibly could off of the table. We would take the highest one we could and the lowest one that we could, and that would get us the greatest voltage. And you can take a quick look here that the farther in we go with fluorine, we go from 2.87 to 2.07 with the next one down with the reduction of ozone. Similarly, on the other side with fluorine, with lithium, pardon me, when we go from lithium to potassium, we go from negative 3.05 to negative 2.93. So the numbers are going to get smaller the farther together we go. So now what I really need to do is I need to find what the problem was asking for. So I've got magnesium, aluminum. This is going to take me a couple times back and forth to find all these. Magnesium, aluminum, zinc, iron, copper, silver. Yeah, it's going to take me a little bit to find all these. So copper, because I do want something that's going to be copper solid. So here's copper solid. So here's copper solid. I don't think I wanted lead. Let's also, iron solid, right? That was copper solid. This is iron solid. I want the iron solid. There's zinc. Aluminum. I think I'm missing one. There's magnesium. Silver, I think was the last one. So 6 of them. Magnesium, aluminum, zinc, iron, copper, silver. Oh, where's the silver? There it is. So as you might have noticed, I've been using all black arrows for everything that I've done, and I did basically put arrows to all 6 components. So now what I'm going to do is I'm just going to widen this out to figure out where my 6 arrows are, and all I want is I want the top, the one highest up and the one lowest down. So here's a high one. Actually, let's use not pink for that. Let's use a different color. I'll use blue. So I want whatever this thing is, and I want the one lowest down, whatever that one is. So for me, that is silver at the top and magnesium down at the bottom. And I'll go ahead and zoom in so you guys can see that. So silver here at the top and magnesium down here at the bottom. And all I was looking for was the biggest difference. What's the biggest difference far away from these two I can get? I want magnesium and I just forgot silver, magnesium and silver. There it is. Phew. So all conceptual. And if you wanted to, you could have figured out all the values. So if you really wanted to, you could have actually sat down and done all of the math for each and every one of these and then figured out which one was the highest voltage. So if you wanted to do this numerically, you could have gone ahead and calculated that a couple of times. Now, I didn't hear back from the chat, but I assume that the other question that the person was interested in was number 13. Um, oh, and I just realized I didn't actually grab the key. Oh well. Um, so let me grab the key real quick to just double check because we all like to see that all of our hard work is correct before I move on. But while I'm doing that, basically, again, I'm actually recording this before I've gotten any follow-up questions from the living learning community. Um, so I'm going to cross my fingers that the person that was curious about 31 on the old exam, that it was in fact number 13. I know it's really easy to do when you're typing really fast, is to just transpose those numbers. So that's the assumption I'm working off of. And if I'm wrong, I'm sorry about that, but I got to make some sort of assumption somewhere so we can move forward. Okay, so I'm just going to take a screenshot of this because I'm just currently sharing one window. Boom. But we are correct. It is magnesium and silver. Yay, magnesium and silver. So hard work paid off. Well done. Okay, next question. 13, calculate the value of the cell potential at 25 degrees Celsius for the following unbalanced, it even tells us that, look at that, unbalanced reaction and conditions. And it gives us some conditions. So since these are not at 1 molar, that's the thing that actually tells us that we need the equation with Q, because we are going to need something that will let us put different concentrations in there. And the only way we can do different concentrations is dealing with Q. The other thing is it does go ahead and tell us that we're at 25 degrees Celsius, which means we can use the log version, the one that has all of the constants rolled together. And while I haven't looked yet, I bet that's what this key does, because as I mentioned, it's very popular among the instructors. I don't know why I'm such a big fan of the natural log. I think because most of the other equations have a natural log in them, and I just personally don't like switching back and forth. But I know everybody usually likes to get as close to the exact value as they possibly can, and I'm telling you, when they can, the instructors, the team usually uses the log instead. So that's typically what we use when we make the key. I do, however, go back and double check since I'm a big fan of the other one. Okay. So we have 3 different values that we need in this equation because we want to calculate the value of the cell potential. So that's E cell. Oops, could have written the word cell in there. So that's E cell. So that's what we're looking for. Then it says we've got 3 other things in this equation that we don't have right now. So one of them is the standard E cell, one of them is the number of electrons, and one of them is Q. So as we go through this, what you might actually notice is that we do actually have one of these. So we want E cell and E cell standard, and that is given in the question. So we do have one of these. We do, in fact, have one of these. Oh, it didn't trade off. Hold on. Get rid of my highlights. This is a problem I have every once in a while with OneNote. So cell potential, and the other things. So I have the standard that was given in the problem. That's very lovely. So my E cell standard is right here, this 2.20 volts. Then I need Q and I need N. The nice thing is that to calculate these, I'm actually going to just do one relatively long step that will get us both of these pieces of information, because part of what I'm going to need is the balanced equation. So what I am going to take a look at is this equation. What do I have? And is it balanced right now? Now, there's a couple different ways to do this. I'm gonna do it the long way first and then see if we can find a shortcut. But perhaps show off why I like the long way first. So this is iodine as a solid going to I negative and aluminum solid going to aluminum 3 plus. When we look at this then, we want to make sure that our elements are balanced. In the iodine, they are not. So we're going to add a 2 here. So then I have actually 2 -1 charges here on the right. So I need to add 2 electrons here on the left. My aluminum, I have a +3 charge here and neutral. So to balance that, I need 3 electrons here. So then when I look at this, I have that problem again that things are not balanced. So I've got 3 electrons and 2 electrons. So I need to balance this by multiplying by 2, this with 3. So that's going to be 6 electrons plus 3 iodines goes to 6 I negatives. I'm going to bring this other one down here. 2 aluminum solids going to 2 aluminum 3 plus 6, because I'm multiplying, 6 electrons. My 6 electrons cancel. And since my 6 electrons cancel, that's what N is equal to. So those electrons that I'm canceling out, that is in fact my value of N. So that's how I know it's whenever I get to eliminate those electrons, that's my value of N, the number of electrons being transferred. So then over here, I have 2 aluminum solids plus 3 iodine. That's actually still a solid. I'm going to need my states of matter. So I'm looking back up here, double check. Goes to 6 iodine, that should be aqueous, plus 2 aluminum 3 plus aqueous. Yep, aqueous and aqueous. So I found N. Now I can actually get Q. So for Q, all of my solids I'm not going to have in my final reaction. So what I am going to have is I'm going to have my iodine to the 6th power and aluminum to the 2nd power. So I was mentioning trying to find a faster way to do this balancing, and that is not impossible, but it can get kind of complicated. So let's take a look at this real quick. Because really, what we need to do is make sure that everything is balanced and care about the charges a lot. So one, I do have to make sure I've got 2 iodines, otherwise everything's all messed up. And then really what I usually do is I just typically think about this as oxidation. So I've got 3 electrons going here, and I've got 2 electrons to do that because I have 2 electrons total, 1 for each iodine atom. So now I can see 3 electrons, I can see 2 electrons. That means I need 6 electrons. Not necessarily in one particular place, on both places. I guess I could draw it on both places. Now, the problem here, though, is that since what we really need is Q, getting this balanced gets a little bit tricky. I guess 3 electrons for aluminum, 6 electrons total. So I'm going to put 2s here. And again, 6 electrons total. So I'm going to need to multiply my iodines times 3. That's a 3, and that's a 6. So it's possible to do it a little bit shorter without doing the half reactions, but realize that I basically thought about the half reactions. I just didn't write out the half reactions. So it's up to you. Personally, I like to just write out the half reactions because that winds up being the thought process I go through anyway. Okay, I got an expression for Q. I need a value for Q. Hopefully, there we go. I got numbers. So iodine is 0.18 to the 6th power, and aluminum is 2.5 times 10 to the negative 3. 2.5 times 10 to the negative 3 squared. Oh dear. .18 to the 6th power. I get 3.4. I'm just doing this individually, so basically if anybody notices later that I messed up the math on this one, we can find it faster. times 10 to the negative fifth. I'm just going to do that one more time. To the sixth. Oh, that looks good. And 2.5 times 10 to the negative 3 squared 1.5625 times 10 to the negative 8 and multiply those two things together. I'll also fess up that I am checking the key every once in a while because this problem is very long and I actually haven't had my cup of coffee yet, which might be my mistake. Not happy. Oh, sorry, that's my alarm. Let me show you guys what I'm looking at. Maybe this is why this person wanted this question. I'm just gonna nab this. So this is showing my Q value. So it's looking like I balanced everything fine. So there's the aluminum being multiplied by 2, the iodine being multiplied by 3. Here's my total reaction. Then as promised, there's my E cell using the log version. There's the 2.2 volts for E standard of the cell. There's 6 electrons for N. Then there's my Q expression, which is that all over 1, which is what I thought I did. 2.5 squared, 0.18 to the 6th. But that somehow is not what I got, because this phrase in the log should be what I have, and I have 5.3125 times to the negative 13. So somewhere something's wrong, and I'm not entirely sure what it is. What I think I'm going to wind up doing is proceeding with both sides of the math to see what's going on. 1/8 to the 6th power times 2.5 to the negative 3 power. Squared. Oh, now I get this value. So something's wrong. Yeah, sorry about that. So something's wrong in my math. My apologies. I do in fact get all of that to equal 2.13 times 10 to the negative 10. Be wrong. That looks like that. 5, negative 3 squared. Oh, yeah, I don't know how I did it, but this squared term I had was wrong. So this part was what I had done wrong, so that's not it. So should be equal to 2.13 times to the negative 10. Then we just plug everything in. Aren't we excited about that? So I was mentioning when I did the problem from the review that this problem just winds up being fairly long. And it is. So now what we're going to do is we're going to take all of this stuff that we were working on before and plug everything in. Oh, come on. So from the problem, I have E standard of the cell, 2.2 volts minus 0.0592 divided by 6, that's the number of electrons, times the log of Q, which after much struggles is 2.13 times to the negative 10. Also, I should have figured out this was wrong because 2.5 times to the negative 3 squared should just be a 10 to the negative 6. That exponent math there should have clued me in. So now we just plug everything into the calculator. So log of something that's really small, less than 1 is going to give me a negative number, times all of this stuff. So this entire term should be positive. So my E cell value should be positive overall. So 2.20 volts is going to be minus and negative. So adding those together, 9.67 divided by 6 times 0.0592. But something relatively small. Looks about right. Double check over here. Okay. Because basically this is essentially adding 1. So when I get 2.2954, this is just going to round to be 2.3 volts, which is the same. So yeah, my apologies for the problems with my exponent math. But that is how we do the problem. Notice in here that when they even broke this down for points, that just finding the number of electrons by itself was worth 1 point. Finding Q by itself, which would have just been this conglomeration, was worth 2 points, and then the rest of it was worth 2 points. So I would have scored a 4 out of 5 on this because I had everything set up correctly and messed up my math, and that's usually worth -1. So hopefully this helps. And these are, as I mentioned, the longest kind of problem. So do them carefully, do your best. Good luck.